Hello people, in this video I will be presenting my solution to the first problem of INMO 2024. So as you can see, this is a geometry problem and I think it was fairly simple considering INMO standard. So let us try to see its solution. So first let me draw a circle because a circumcircle is involved here, and let's make it a little bigger. Yeah, so we are given that in a triangle ABC, CA equal to CB. So I am drawing C at the top so as to make it look like an isosceles triangle, and these are the points A and B, and we are given a triangle CAB with CA equal to CB. Wait, I'll yeah, CA equal to CB, and point E lies on the circumcircle of ABC such that ECD equal to 90 degree. So basically we have to draw a perpendicular line to C and touch it at the circumcircle. So this is the point E, and the line through E parallel to CB intersects CA at F and AB at G. So they are talking about this line, something like this, and we know that these lines are parallel. And the intersection points are given by CA at F. So this is the point F, and this is the point G. Prove that the center of the circumcircle of EGB lies on the circumcircle of triangle ECF. So EGB, let's denote it circumcircle by O. So O is the circumcircle of triangle EGB. In other words, it's the intersection point of the perpendicular bisectors of EGB. Okay, and we need to prove that it lies on the circle joining this particular circle, the circumcircle of EFC. Okay, so this is what we need to prove. And now let's begin with the solution. To begin with, I want to make a few observations. Notice that we are given that this particular angle is 90 degree. And now if we join A with E, then this particular angle will also become 90 degree because of course BE will become the diameter of the circle, and thus EAB, which is this white angle here, becomes 90 degree. Okay. Now let's chase some angles. Say this angle we denote by 2 alpha. It will become clear in a moment why we denote it by 2 alpha and not alpha. So let's draw a few more line segments. So notice that angle ECA equal to angle EBA by properties of a circle. So this angle also becomes 2 alpha. Okay. And because this angle is 2 alpha, and note that we know that angle CAB equal to angle CBA, because this follows because ABC is isosceles. Okay. And also we know that angle ECB equal to 90 degree by the problem condition, which implies that angle ACB equal to 90 minus 2 alpha. Okay. So what I'm talking about is this angle. This angle here becomes 90 minus 2 alpha. And because we know that angle CAB equal to angle CBA, so this angle becomes 45 plus alpha, and this whole angle becomes 45 plus alpha. Okay. This whole angle becomes 45 plus alpha, and if we deduct 2 alpha from here, we get that this angle is 45 minus alpha. Okay, this is 45 minus alpha. Now notice what happens in, now notice this small triangle, EAG. Let me draw it to make it clear. This particular triangle, we claim that F is the midpoint of EG. Okay, so we will do it by proving that F is the circumcenter of triangle EAG, and thus we know that in a right angle triangle, the circumcenter is the center of the hypotenuse. So we will be done using that. Okay. So now let's chase a few more angles. We know that this angle here is 45 minus alpha. So because EG is parallel to BC, we can also get that this angle here is 45 minus alpha. Okay. So this angle here is 45 minus alpha. And using the fact that, as I had proved earlier, this particular angle is 90 degree. So this is 45 minus alpha. This is 2 alpha. So a quick angle chase shows that this angle will be, this is 2 alpha, this is 90. So this has to be 90 minus 2 alpha. 90 minus 2 alpha. So this angle is 45 minus alpha. Okay. This angle is 45 minus alpha. Also note that this angle here is equal to this angle here, of course, by angles in the same segment. So this angle becomes 45 minus alpha. And now if you notice, the we are forming an isosceles triangle here. This is the isosceles triangle, and hence this side will become equal to this side, and of course this is equal to this side. You can prove that very easily. So F is the center of the circle of A, E, A, and G, and hence F is the midpoint of the hypotenuse. Now notice what happens in triangle EGB. In triangle EGB, F is the midpoint of EG. So O, which is the circumcenter of EGB, lies on the perpendicular to EG through F, because of course it lies in the perpendicular bisector. So let's draw F and O, and of course this angle is 90 degree because this is basically a perpendicular bisector. FO is a perpendicular bisector. And now to finish the problem, we will join EO and GO. Okay. Notice that in this triangle here, EGB, this angle is 2 alpha, and O is the center of the circle of EGB. So of course the angle at the center of the circle is twice at the circumference. So this angle will be 4 alpha. So angle EOG, which is this small angle, is 4 alpha, and we know that this line is the perpendicular bisector. So this angle becomes 2 alpha and this angle becomes 2 alpha. Okay. And now notice what happens in these angles. EOF and ECF, both of them become equal to 2 alpha, and hence by angle in the same segment we know that O lies in the circle of EFC. So we get that EFOC are cyclic, and this is what we needed to prove in the problem. So yeah, this was the solution. Thanks for seeing the video.